All right, last session we started with the first part of our third model, which was logistic regression. So we're going to continue with that with the second part, and mostly we talk about the iterative method that we use to solve the logistic regressions problem for its solution, and that's gradient descent. So let's just have a recap of what was told last session. So as I mentioned, logistic regression gives you a probability between 0 and 1. So when you predict a true value, a correct value, with high confidence level, or what we say here with high likelihood, which means that the probability was high. So when you predict the correct value with a high probability, thus your error will be reduced. So you're going to have assigning high probability to true labels will reduce their loss function. So the last word is loss. On the other hand, another good point on the other extreme of the graph, if you remember what was like, so it was like this. So we had this, and here it was 1, and here it was 0, and here it was the half, right? So we're talking about these two extreme sides now. For the function. So on the other hand, if you assign high probabilities to incorrect labels, so you were sure that something would happen, but it didn't happen when you check your data set, and you were wrong. Thus, if you if you compute the loss function, you're going to have an increased loss function in your loss. So as an example, I mentioned last session, suppose you have xn of d plus 1 R space, and the output of the logistic regression was, so we had the probability of W of -1 for given the xn equal to 0.8, and the probability of true values, true labels, given xn was 0.2, right? You see that the probability of true values are lower here. So we gave them less chance for that to happen when we train a model. Thus, if you calculate the loss function, the En of W, for the case that Yn was 1, so you had the true value, so you had the condition happen such as the patient is sick, or the patient is when you took a look at your historical data, you found out the patient was actually had cancer, or he was sick given those characteristics. So because of that, when you compute the loss function, you're going to have 161 on the case of +1, which is fairly higher than 0.22 for the case of another case, which was -1, and you give it higher probability, right? These two should make sense. When you give a higher probability to certain feature space, and the true label was correct, or correct in a sense that it was +1 and you predicted +1, or it was -1 and you predicted -1. So you're going to have a variance between your loss functions. Also, for the typo of the previous session that you asked, thank you for that. So I corrected that, and you're going to find it in your slides. So if you take a look at the slides, so they are there up to lecture 7. And I think it was the slide number 12. Also, I've uploaded the first 7 lectures online, so you can find the recorded sessions there as well. All right. So yeah, as I mentioned, the loss is smaller for the case Yn, which was -1, because we assign higher probability. All right, now we're going to see how we're going to minimize the loss function. So the loss function that we define, we try to understand first what is it, what is it exactly, and then how we're going to minimize it to find the optimal solution, or our W star. All right, we call it, as always, in-sample error of W, the vector W. So given x1, y1 up to xn, yn, we are interested in finding W, the vector of W, in d-dimensional space of R that minimizes our En of W, and we have to have the summation of all the average E of n, which was the loss function for each of those values from n equal to 1 up to n. And then if we add the values for that En that we defined in last session, so you're going to have 1 plus E minus Yn, E to the raise of Yn, W transpose, and also the multiplication to xn. So let's talk about some common characterization for that. If you draw the graph, so your x-axis pertains to your x's, and y is your f of x. So suppose this is your function that I mentioned last session. It's a convex function, and a convex function was given any 2 points you define. When you draw a line, it's going to be either inside or on the graph. So since we're talking about the probabilities and the function is convex, so we can have additive across training samples. So this word is additive. And just like the linear regression, we can regulate that function by hyperparameters of lambda. So you can apply that in order to regulate the way we're going to add those training samples as a variant of your logistic regression. And as I mentioned, is E of in-sample error of W is a convex function of W. So we can apply optimizations with this. Now, since logistic regression gives us some nice probabilistic properties, so we can define another way to sort of find the performance of our model, and intuitively it's sort of an inverse version of probabilistic model. So we call that likelihood. So let's talk about likelihood or maximum likelihood here. So if we talk about in a probabilistic model, such as logistic regression, we try to find the most probable hypothesis given our data, right? So given the data, we are trying to come up with the most probable hypothesis. But if we define it in a likelihood word, so it's exactly vice versa. So how likely is it to find the data from the hypothesis? So the other way around. So with the likelihood, given our vector of W, we desire to find the probability of data given a hypothesis. So we are going sort of an inverse path, sort of a reverse engineering to define another metric called a maximum likelihood. Oh, let me just go back here. And it's very intuitive in many applications when you use a probabilistic model, so that when you consider a hypothesis was true, like if h of x was a specific value, how are you going to drive with your data out of that hypothesis? So it's exactly the inverse version of the probabilistic approach. I'll have an example later on, you're going to see that. Also, for those who were interested in knowing what sections are we talking about today, we are talking about section 3. The 3, so logistic regression. We hope that we're gonna reach some good portion of gradient descent, and probably by next session we're gonna be done with the linear model. And next week we're gonna start neural network. All right. Oh, let me just close this and reopen it. Okay. So as an example, if we assume H was F, so our hypothesis was actually the one that we found that it was true. So how likely is it to get Y, the value, the true label, from our X data, right? I'll let you think about it for like 10 seconds to see the flow here. So we are going backward now in likelihood. So if you assume our hypothesis was F, actually, how likely is it to get the true label of the data from our data, right? It's the other way around now. All right, so as an example, if the probability was high that we computed with the assumption of H was F, which means that we did a good job. So so we had a high probability, and the hypothesis was actually F. So it's a plausible, situation for us because we had a good assumption. Otherwise, if we had high probability and H wasn't F, so it means that our assumption was poor, right? Just like the example I mentioned with a higher probability and lower level. So the losses were different in those two cases. So if you sort of formalize it, so the PR or P, the probability of Y given X is going to be either F of X for the labels Y plus 1 and 1 minus F of X for the Y equal to minus 1. So assuming that H was F given a data point, so we can find the hypothesis H of X for Y plus 1 and 1 minus H of X for Y minus 1. All right, now we're going to formalize it. So the maximum likelihood approach finds our W vector in the, that's actually D plus 1. D plus 1 that maximizes the probability of all the Y's given our X's, right? Given our data. So we are trying to maximize this function. So 1 over n of log this probability, and that is equal to, again, maximizing 1 over n, the log of, this is the product, because we are talking about probabilities, so we have to have the products of all of those, all of the y up to n, yn given xn, right? So like multiplying py1 x1 up to yn xn. So, but in most optimization problems, also for the loss function, we are interested in minimization, right? So how we gonna change this to a minimization problem? First, let's get rid of the products there. So one of the properties of log is when you you can change this product to a summation when you because actually the log of a product is equal to the summation of those, right? It's one of the properties of that. So we can change the product to summation here. And then remember, still we are in the maximization problem. So by adding, when we maximize something, the invert of that, so the minus of that is going to be the minimization problem. So if we add minus log here, so the maximization problem changes to minimization. So now we have 1 over n sigma from n1 up to n minus log of pw, p hat w, ouryn's given our xn's. And finally, you're going to have the 1 over n summation of n equal to 1 up to n, the en, which is our in-sample error for the vector of w. All right, so in statistics and also machine learning, we have another notation for computing the loss function, and it's mostly referred to as log loss, so the log of your losses. In signals and signal processing, sometimes they refer to it as the number of bits you need in order to encode a signal, because log refers to, in a binary space, when you have like 128, so it's going to be to the raise of 7, so the log would be 7. So with 7 levels, you can encode certain bandwidth of the signal. But here, we're talking about continuous word, so we can also use that within the probability we have. So it's called cross entropy error or log loss. So the definition, I mentioned it there. So it measures the performance of a classification model whose output is a probability value between 0 and 1. Okay, so now we're going to see how we're going to relate the in-sample error to that. So we had this in-sample error of vector w, which was 1 over n. Our n's were from 1 to n minus the log of the probability we have, yn given xn's. So we can expand this for the case. So that was, as you know, that was the indicator function. So it's going to return the value. If it was 1, it's going to return it as it is. If it was minus 1, it's going to return it as minus 1. So the indicator function of log 1 to the denominator of p hat w at 1 given xn plus the other case, the case that yn was minus 1, and that if you sum these two up, we're going to have the summation of natural log of y 1 plus e to the raise of y n wt xn. And that was your actually the idea of your hypothesis xn and yn that we talked about with the likelihood. So you see that in different ways we can define our error measurement, the loss function, the cross entropy, and also our likelihood. Questions?
So for the probability, let's say for the probability that y equals 1, given x, right?
So now that we define the loss function, the cross entropy, and the likelihood of the function w, the vector w. So now we're going to see how we can find the solution for En of w. So you recall from your linear regression that we use least squares because linear regression was a closed form. So first of all, it was first order. So you could feed a line given your data. You could feed a line, and using least squares, you could minimize the sum of all these errors to your data points, right? And it had an analytical solution to that. So here we're going to have another challenge in which this function is no longer a first level, it's a first order linear problem, right? It's not a linear problem. So we're going to end up not being able to have an analytical solution to find the W star as our the solution of our minimization. So we're going to see how we can tackle these type of problems using an iterative method that approximate the solution for us. And that is the gradient descent that we're going to learn now. So as I mentioned, that was the error measurement of our hypothesis xn. So this is our h of xn and the given y of n. As you see, this is a property for that. So it is called. It doesn't have a closed form solution, but this one had a closed form solution. So LR is linear regression. So just like LR, it doesn't have a closed form solution. So make sure this is it doesn't. Thus, we need to use some iterative methods such as gradient descent to find solution. Step by step, we find to converge to a good solution. So suppose this is your optimal x that corresponds to your W star. So you start from either of the side of the graph, and you want to find some method in order to descend into your function and find this spot. There are so many factors involved. I'll describe them all today. So how are we going to find the steps here? What kind of steps we want to use in each of the iterations. We want to make sure we don't overshoot and just take a huge step, just wobbling here and there like this. This is not good. Like taking huger steps towards the end, we might even pass the solution, right? And this is not good. So we want to make sure we have good number of iterations towards the final solution using a gradient descent. And yeah, we're gonna learn about it today.
Yeah.
All right. So in an unconstrained minimization, we are trying to minimize f of x given x is from our n-dimensional space of R. So typically our f is differentiable, is x, so we can, so that's good. So we can apply, we can take derivatives and gradients for that matter, but it does not. But you know, in a closed form solution, which is not in this case, you know, we cannot apply the direct analytical model for that minimization, so that may not exist. All right, so we're gonna go for a numerical approach. So this is numerical, and that is gradient descent. So come back. All right. Yeah.
Gradient descent, how do you know that you fit a global minimum versus local?
Yeah. So that's one of the problems we're going to talk about it. Yeah. There are some tweaks that we should do in the function, and they're pretty easy actually. Okay. So that's your function, and these are two values, x1 and x2, and xw was, as you see in this this situation, was the minimum or the minima, and in this case it was the global minima, right? Also, as I mentioned, this is the convex function. So if we take the f prime of x, or the first derivative of f given our x's, so we're gonna have three situations, right? First one would be the x that we chose to take the f prime was actually our x star. As you see, the x star is the global minimum, right? So if that would be the case, the result of this would be equal to 0, right? It shows that at this point we have 0 slope. So here, thus it shows that f of x at the point of x equal to x star was the minimum. On the other case, if the x's that we chose was greater than or after the x star, which was going towards x2, if you take a look at the function, so the slope is getting increased a little bit, so it's going upward, right? So this result would be greater than 0, so that we can understand that fx is increasing. On a third case, which is the other case, before x star going towards x1, we see that the f prime x or f dash x, so different ways to call it, is less than 0, and fx is decreasing, obviously, as you see. So we can use this in order to build our way that we're going to go for iterations in gradient descent, in which direction we go, right? All right, so as a very intuitive way to describe numerical method for a gradient descent is, so suppose this was your function again, x star was your global minima, and we want to make sure these blue lines are the steps we are taking. We want to make sure that we start depending on the slope of the function. If the slope was higher, we normally take a huger step, a longer step, and then when the slope starts to decrease, so we lower the amount. But if we go too much, we're gonna get past the global minimum in this case, and that's called overshooting. So we want to make sure we don't overshoot. So the algorithm goes as, first we're gonna initialize our starting point, x0. So it could be any of the points in the graph. Sometimes in order to get past some of the global and local, we need to restart from different starting points. Because sometimes, in the case of logistic regression, it might not happen, but in other higher order polynomials, when you have several, so this is a local minima, this is a local minima, and this is a global one, right? You might just go there and you might be stuck there. And since you're going to have an increase in the shape, so the gradient descent might find, okay, here's your solution, and I'm just stuck here. So sometimes you have to reiterate, you start with another point as your x0s, or just here, to find a solution. But surprisingly, we have found in practice that even those points are working pretty well, although they're not bringing the best solution for us. So we're going to see what we can do normally in this type of situation. So I defined 3 different cases that we can modify the algorithm in a way that we can find the global case. All right. So as I mentioned, we're going to initialize our x0. If the slope was 0, so we didn't have an increase or decrease, that means that we already found some, so we have to stop. Otherwise, for those 2 other cases, when f dash or f prime of x was greater than 0 or was below 0, so we have to find a step, that we call it E here. You can, in other textbooks, you might find it with different names like n, eta, or whatever. So here we call it E or epsilon, and that's your step size. Just like the blue line you have in your graph. So if you take it super slow, you're gonna have a slow progress. So you're gonna go like this. So several iterations it takes when you reach it. If you take it huge, you might overshoot and get past it, right? So thus you're gonna have low accuracy.
So just to clarify, so I thought x was like your data points. With gradient descent, are you trying to modify your weights?
Yeah, I mean, just think about x as as x and y in a function of your w. So just and then we carry on iterating over these algorithms and going to step 2 again and check. So we can define k as the number of iteration to practice. and it's equal to epsilon of k is almost equal to 1 over 1 divided by k. So initially you are interested in having a higher values for epsilon or e, so that the descent becomes faster, so that this one, the first one, but later this e becomes smaller so that the accuracy will higher, and we can find the minimization of the function without overshooting. All right, now let's see in a vector format word, in a vector valued word, how we're going to define this. Again, it's another way of representing the gradient descent. All right. So this is your convex function given two x's here, two features, and that's your f of x, y, and f of x1, x2. So you see that convex function over there, which is this one. So if you start from here, that corresponds to your x0 point here, right? And you want to make sure you want to go down the descent up to the x star, which is your global minima, right? So the next logical step would be going towards this to your x1, right? So you have to traverse this. If you project it to your x axis as this space, that means that you started from here, you went that direction, and you went to x1. So that was our x, that was our epsilon, which was the step size. And the direction in vector world is going to be defined by this u vector, right? U is a unit vector. And as you know, unit vectors are defining the spatial direction for us, just like this. It's going to define the direction towards x1, and normally they are the value divided by norm, right? There's u. Oh, let me clear this. So given x0, how should we take the next step? So we go towards x1 from x0 by epsilon u or mu, and our vector of u, our unit vector, is going to show us the direction in which we're going to go. Yeah. And that's the definition of that, the unit vector. Now, we're going to run into a problem with this algorithm, because when we go past the x1 towards other x's, how are we going to find exactly what's going to be the f of that point on our convex shape, right? This parabolistic parabola, I think I call it. So, and for that matter, we need to use an approximation function to estimate the point in which we hit for the second time or the nth iteration. And in order to do that, we have to use a Taylor series, right? I'm sure you've already been thought about this series, right? Taylor series? You know what it is? I mean, I have some recap slides in order to summarize it. So basically, Taylor series approximation works when you want to approximate your f of j's, f prime of j's, given the points you are having, like f. So you want to know what is the f prime j for the point xj. So using the other points and using the other values, how are you going to define their f prime? So given the place you are inside that graph, you have three options, right? Either you go forward difference. So forward difference from this one forward. So here. So the distance was delta x1. So in order to approximate that, and this is an approximation, you need to have the value of fj1 divided by the distance between these two, right? Which was wx1. If you were here and you wanted to compute this, which was the backward, here. So in order to f prime j or f dash j, so the distance was wx2. I just wanted to make sure that these two could be different, but in general you can assume that this could be, if you had the steps would be equal, these two would be delta x. So I just mentioned delta x1 and 2. So the distance is delta x2, and in order to compute f prime of j, you have to subtract fj1 minus from fj. And a third way, depending on the situation you were in your graph, is centered difference. So in centered difference, you want to, so the distance would be here. That's why you have x1 plus x2. Or if these two were equal, it would be double delta x, right? And that would be this one minus this divided by the distance. Let me make sure formula is correct. This was actually prime. I'll fix it in the slides when I upload it later. So make sure this one had the dash there. All right. So given on the place you are in that graph and the different points you've computed, so you have three different ways to use Taylor series approximation, right? Forward difference, backward, and centered. So now let's go back to our gradient descent and the problem we were trying to minimize. So we can use that Taylor series approximation to derive the estimation of our derivatives and find their order of accuracy. So, as you know, it's a series of equations, and the further you go, the more accurate you are. But definitely, you're gonna have to compute more and more stuff. So, in general, if you want to compute the point fx plus delta x, it would be equal to fx plus delta x f prime x. And now going to the second order, so you're going to have delta x2 divided by 2 factorials, f double dash, or the second derivative of x. And then we go further to the third order, and then this can go on and on and on. So the more you go further, you're going to have more accurate approximation of the point you wanted to calculate on your f, which was here. So if we expand it to our problem, so we were interested in estimating the f of x1 for our minimization of the logistic regression. So expanding that on x1 using the Taylor series give us this f of x1, which could be starting from other x's plus delta x, right? So it's going to be f of x0, the starting point, plus our step size with the direction that the unit vector gave us, and that's equal to f of x0 plus epsilon u hat u dash, the gradient of fx0 plus the rest of the things that we are not interested in computing right now, because this gives us good enough of point of accuracy. So that's why we call it order, and that order can be computed as either n2 or n3 or n4. So we call it the rest as the order of certain, complexity. So now, given this is known to us, this is known to us, but we are interested. Now we have to compute the gradient of fx0, right? So you're going to have another slide about that, and I'll stop after that. Yeah.
Can you explain why this you have to order?
So this order of this, it defines the complexity of the rest of the things that we left out because we are not interested in going further, right? We might be able to spend 20 more equations here to just gain maybe this amount of number for accuracy, but it doesn't work in this case. All right, so let's see how we're going to compute that gradient here, and that's going to be it's going to be equal to the derivatives of f divided by given x1 of the point x0 up to all of them up to xn of x0 in our n dimensional space of R. So this u was the unit vector. As I mentioned, it was showing the spatial direction, and always it has the same direction to our f. In this case, because we are defining it as minus, so it's going to go the other way around. But this shows a spatial direction, and that's why I put this circle around it. So this spatial direction is shown by this unit vector. All right, thus we pick the unit vector to minimize the first order approximation. And it would be equal to the norm, the real value of the gradient divided by the norm in a minus. So that's why you have a different. So you have the direction going down here, and your f was going up. And finally, you have for the gradient f of x, the points in the direction where f of x has maximum growth at x equal to x0. So I'm going to stop here, and then we're going to see next session how we're going to use this in order to apply our gradient descent. Later on, we see what are the variants of gradient descent, like the stochastic gradient descent. We have batch gradient descent and other things. And then we conclude with the session of with the whole section of linear models. Okay.
Are they from this book or online?
If you take a look at your corpus, there have been some of them are from this book, some of them are from Boyd, and some of them from Deep Learning book. So all those three books that used to be your
Even the recommended ones?
yeah, all those three. But mostly they are from here. But anyways, anytime you have an assignment, they're gonna post you the text as well. If you take a look at it, you're gonna find it in your module. Right.
Is epsilon the learning rate?
No, learning rate is gonna affect epsilon later as another
Okay, so epsilon
hyperparameter.
is like learning rate